Swayam Prabha. Digital India. Educated India.
Hi friends, now we will discuss on the topic gaseous fuel syngas production from natural gas. In the previous class we have seen that natural gas can be used conventionally for the heat application, or it can be used in power plant for electricity production. We have also discussed that this can be converted to syngas and then syngas to different types of chemicals including hydrogen. So, if we can do it, then we can reduce emission level due to the utilization of syngas. In this class we will be focusing on how the syngas can be converted to, how the natural gas can be converted to syngas. Next we will discuss how the syngas can be converted to liquid fuel and also how we can get hydrogen from natural gas. So, the contents of this class is your reforming as a cleaner route for natural gas utilization, then types of reformers or reforming, that is SMR, dry reforming, ATR, CPOX, by reforming, dry reforming, etc., and then comparison of different types of reforming and then reforming reactors. If we see the reforming, that means that it will be reformed, the molecules, the methane will be converted to other molecules. In this process the syngas is produced, hydrogen and CO containing syngas by the thermal process. It may be exothermic or endothermic, both reactions take place in this, and depending upon the nature of reforming process, the del H value changes, and normally it is a catalytic process, but without catalyst also the reforming can take place, and if we use catalyst we will get better performance. And what is happening by this process, we can eliminate the oxygen from the initial fuel mixture, that improves the overall system efficiency by minimizing energy losses from catalytic conversion. And this product which we are getting, that syngas, this will be used for heat application, for steam generation and for different types of chemical synthesis. So, that is the major advantage of this process for the conversion of natural gas to syngas and then syngas to other chemicals. So, this is our reforming process. CH4 will be reformed to CO plus H2, that is called syngas. Then we can get different types of reforming process as you have mentioned, and the most important are steam reforming, then partial oxidation, autothermal reforming, and then dry reforming or combined reforming of methane, that is called bi-reforming, and then tri-reforming of methane and reforming with membrane. So, these are the different types of reforming processes available in literature, and some of these are applied in commercial scale and some of these are still under development stage, and the first three are mostly used in industry, other these are under development and demonstration scale, and these will be having better feature for the control of carbon dioxide. Now, we will see what SMR is, that is steam methane reforming. So, in this case we will be using methane and steam as a reaction agent, reacting agent, and the reaction will be CH4 plus H2O, both will be in gas phase, it will give us CO and thrice H2. So, this one SMR1 reaction, in this reaction we can get 206.2 kilojoule per mole energy. This is required, this energy is required, that is endothermic process. And then another reaction may take place, CH4 plus 2H2O, that is CO2 plus 4H2. So, carbon monoxide can be produced, carbon dioxide also can be produced, and here 164.7 kilojoule per mole energy is required for this reaction. And then we can get water gas shift reaction in the reforming reactor also, that is CO which is produced here, that can also react with H2O which is available in the reactor and then convert CO2 plus H2. So, this reaction is exothermic. So, overall it is endothermic reaction. And then another important feature is that H2 by CO ratio, this H2 and CO which is available in syngas, the ratio of these two components are very very important, because this will decide the suitability of this syngas for its downstream applications. Different downstream applications require different ratio of H2 is to CO. So, in this case we can get this ratio as 3 to 5. So, the very high ratio we can get with respect to other reforming, and our temperature requirement is 700 to 850 degrees centigrade and pressure is 15 to 30 bar. So, this is a commercial process, and in this process catalyst is normally used. If we do not catalyst, then also we will get some syngas formation, but basically nickel or on ceramic support, this catalyst, nickel based catalyst on ceramic support with or without some promoter or stabilizers, these catalysts have been used in the SMR process. The precious metals offers alternative to the nickel, and supports may be strong, inert, thermally and chemically stable. So, these are the catalysts of the for this reaction, and it requires high geometric surface area and high heat transfer coefficient, low pressure drop and less carbon deposition. So, during this process carbon deposition takes place, and the catalyst should have that property where the low carbon deposition will be achieved. This process we will discuss in detail, because we see here hydrogen is maximum. So, if we want to get hydrogen from this syngas, the steam reforming may be one of the important process or route, and we will discuss in next class in more detail. Now, we will see some aspect of the SMR reactor. So, here is the SMR reactor schematic say. So, we have these are the tubes, that is called reformer tubes. So, from this we are putting natural gas and steam, both natural gas and steam. So, then high temperature will be provided in this reactor. These are the tubes. Through inside of the tube we are having the hydrocarbon and steam, outside we are having high temperature by burning some fuel gas. So, here the burners are there. So, high temperature is generated and there will be some reforming reactions inside the tube, and we will get the product from the bottom of this tubular reactor or tubes of the reformer. The syngas we can get 850 degree centigrade, 20 to 30 bar and 70% hydrogen in dry gas. So, this is the steam reforming reactor, and these are the reactions already we have discussed. Endothermic and exothermic reactions both are available during the process, and overall it is endothermic reaction. Next we are coming to partial oxidation, that is POX, and catalytic partial oxidation CPOX. So, this method is also used largely, and here as you see partial oxidation. So, we will be providing less amount of oxygen. So, CH4 will be converted to CO plus twice H2, that is the required for in syngas. So, then here we can get H2 by CO ratio 2 to 2.5, and temperature is higher 1200 to 1400 degree centigrade, and then pressure 50 to 70 bar. So, here methane will be partially converted to this one, that is one reaction. Another it is possible methane is reacting with 2O2, then it is CO2 plus H2O, then CO2 plus H2O further it can give up CO plus 2H2. Other reactions which can take place here, methane plus H2O which is produced in this, H2O can react with the methane also and it can give us CO plus 3H2, and CH4 plus CO2 which is generated this reaction, that can also give us CO plus H2. So, that is why we can get H2 by CO ratio as equal to 2 to 2.5, and this is exothermic process and faster than steam reforming and requires a smaller reactor vessels. So, advantage of this, we do not need to give much external energy for these reactions. And then if we see the catalyst part, then also we will see the first row of transition metals, nickel and cobalt, and precious metals, ruthenium, rhodium, palladium, platinum and iridium, those are used as a catalyst for this reaction, and the relative rates of carbon depositions are in the order, that is nickel and greater than palladium, greater than ruthenium, then it is greater than Ru, and then it is greater than Pt. So, this is greater than iridium. Okay, so, carbon deposition is a major issue on nickel catalyst which may reduce the number of active sites. So, heavy carbon formation may give increase in the pressure on the feed side, that will be the pores will be blocked, and more pressure drop we will get during the reactions and in the reactor. So, we see the reactor configurations. So, we will be having two zones in this case, the first is your flame zone and another is your heat exchanger zone. So, flame zone means here hydrocarbons, in our case methane, then oxygen, those will be combusted, and possibly low amount of steam react together. So, here some reaction takes place and then CO and H2 form here, and then at high temperature we recover excess heat. So, this is the features of this, but this is for POX, but if we use CPOX, then we can get some we can have some catalyst layer here at the first flame, and then we will be having some catalyst here. So, catalyst will help the reactions. So, conversions of the process will be more than the POX. Then we are coming to ATR, autothermal reforming. So, in this case we use steam and oxygen. So, steam and oxygen. So, the reactions are the methane plus steam, then it will be CO plus 3H2, it will give also CH4 plus half O2, then it is CO plus 2H2, and then this is the heating value minus 36 megajoule per kilomole, and overall it is endothermic process. H2 by CO ratio here we can get around 2, and temperature is 850 to 1000 degree centigrade, and pressure is 20 to 100 bar. So, what we see here are two types of reactions. So, this reaction is basically for SMR and this reaction is for partial oxidation. So, SMR plus partial oxidation basically gives us ATR, and nickel based catalyst have been used for this reforming process. And if we see the reactor configurations, as we have discussed, the first the hydrocarbon or methane will be combusted, and we may use some oxygen and steam here, and then some reforming reactions will take place in this zone. Now, catalyst may be will be available here, and then we will get syngas. So, the reactions already we have discussed that CH4 plus O2, this will be there, and then reforming will be taking place, CH4 plus this H2O which is forming this, and CH4 plus CO2, then we can get this one. So, this is the basics of the ATR process. So, by proper adjustment of oxygen and steam to carbon ratios, the partial combustions in the thermal zone supplies the heat for completing the subsequent endothermic steam and CO2 reforming reactions. That is two reactions which we are getting, this heat generated, that is used in the second case. Next we are coming to DRM, that is dry reforming of methane. So, dry reforming means there will be no steam use, obviously it is carbon dioxide is used for the reforming purpose. So, reaction is methane plus carbon dioxide 2 CO plus 2 H2 in gaseous phase, and this is our del H 247 kilojoule per mole. So, endothermic reaction again, and here temperature 630 to 850 degree centigrade and pressure 1 to 20 bar, and here the H2 by CO ratio is less 0.4 to 1.5, and here we can get nickel based catalyst are used in widely, and presence of CO2 gives rise to more chance of carbon formation. So, as we are using carbon dioxide as the reactant for the reforming process, the carbon deposition is more in this type of reforming process, and that is the major disadvantage of dry reforming, and that is the more challenging part also, and that is why it has not got industrial application yet. And efforts are on to improve this process, how to reduce the carbon deposition in DRM, and development of active catalyst materials, but with a very low coke formation rate either on the catalyst or in the cold zones of the reactor is the main challenge just we have discussed. Then we are coming to bi-reforming. Then in this case we will be using two reforming agent. So, here methane plus steam and then carbon monoxide. So, here we will be having methane plus steam CO plus thrice H2, del H is equal to 206.2 kilojoule per mole, then CH4 plus steam, this reaction can also take place, and then this is the del H is this one, and CO plus H2O, that can give us CO2 plus H2, and other reactions which is taking place here CH4 plus CO2, it is giving us 2CO plus 2H2. So, in this case we can use carbon dioxide and steam as the reactant for the reforming process, and overall is minus 41.2 kilojoule per mole, and H2 by CO ratio is 2, and temperature 7 to 950 degree centigrade, and pressure 10 to 30 bar. So, it more one of the important advantage of this process is that it can use carbon dioxide as a reacting agent. So, it helps to reduce the carbon emission and increase the carbon footprint. And so, here also nickel based catalysts are used, and nano composite, that is nickel zirconium oxide is superior to conventional nickel zirconium oxide. That means, efforts are on to increase superior quality catalyst using nanoparticles for this particular process. And then we will discuss the tri-reforming. So, here we will be using three agents: oxygen, carbon dioxide and steam for the conversion of the methane. That is why it is tri-reforming. So, major reactions are here CH4 plus half O2, CO plus 2H2O, this is your del H value, and then CH4 plus CO2, it will give us 2CO plus 2H2, and then this is del H value, and CH4 plus H2, it will give H2O, it will give CO plus thrice H2 with this heating value, and CH4 plus 2O2, CO2 plus 2H2O, the heating value is this one. So, overall heating value 166 kilojoule per mole, and temperature 1000 degree centigrade, and pressure 20 bar, hydrogen to carbon monoxide ratio 1.2 to 1.5. So, here we are getting tri-reforming, that is carbon dioxide reforming, steam reforming and methane oxidation reactions. So, these are the features of tri-reforming, and catalysts are basically nickel based catalyst, and some examples are given here: nickel, calcium oxide, zirconium, nickel, cerium oxide, lanthanum oxide and aluminum, and quadrate, nickel ceria, and then lanthanum doping. So, these are some example of this catalyst used in this reaction. Now, we will compare different type of reforming processes. So, steam reforming, partial oxidation, and then bi-reforming ATR we will discuss. So, here reforming reactants as we have discussed, operating conditions we have discussed, methane conversions we will see here how it changes, and they are, all of these are having some advantage and some disadvantage. So, that part we will see here. So, steam reforming gives us 65 to 95% of methane conversion, partial oxidation 95 to 100%, and then it gives autothermal 95 to 100% and dry reforming 70 to 96%. So, these are different methane conversions reported in literature. An advantage, as we have discussed, that the steam reforming can give us maximum H2 by CO ratio. So, when we are interested to get hydrogen from the syngas, then this process we will prefer. Steam, as you are using steam, it may induce some corrosion problems also, and that is its disadvantage. And similarly, for partial oxidation, high cost of air separation units, we have to separate the oxygen from the air. So, that is the increases the cost for the process, and no direct heat exchanger is needed, and more compact than steam reforming, and low reformer vessel cost. So, these are the advantage of this partial oxidation. And similarly, autothermal process, we have high cost of air separation unit, and advantage is all heat needed is supplied by partial oxidation, and then this is used for that heat is used for reforming. So, more compact than steam reformer. And then dry reforming, as you have discussed that it uses carbon dioxide. So, that is the major advantage of this process, and conversion of greenhouse gas into fuel or to syngas, and specific ratio of methane, steam and carbon monoxide 3:2:1 can produce a gas mixture with essentially a 2:1 ratio of hydrogen and CO2. So, this is required for liquid fuel synthesis, methanol synthesis, etc. So, that is the advantage of this process, but if we can develop suitable catalyst and coke deposition problem can be reduced. So, this process can be attractive, but this is a challenge for this process. Now, we will see the reforming reactors. So, different types of reactor configurations or reactor types have been used. Out of those, fixed bed tubular reactor, this is mostly used in commercial scale for larger reformer units, and here we see here feed inlet, it goes here and then it goes through this tube as you have discussed in the previous slide. So, these are the tubes through which the feed hydrocarbon and other reactants goes through, and then after reforming it is going for as a product. So, in this case the tubular reactors in the tubes in this reactor the reforming reaction takes place, and the temperature is given by the combustions of the another fuel gas at the outside of the tubes. So, in commercial scale if we see, one furnace contains 500 to 600 tubes with inner diameter of 70 to 130 millimeter and length of 7 to 12 meter, and conversion section methane and steam are preheated to 500 degree centigrade. Then there are some radiant sections and catalytic sections on the catalyst used for the conversions of the methane to syngas. It is top fired, it can be bottom fired, it can be terrace wall side fired. So, it can be the feed can be at the top, bottom or side of the wall, anywhere it can be done. Then we are coming to microchannel reactor. So, these are the latest development of on this technology on this reactor part. If we use the microchannel, then the performance or economics of the process can be improved, because it reduces the mass and heat transfer limitation. So, if we can reduce the diameter of this, it is almost similar to say tubular reactor, but if we can reduce the diameter very small, and then we can coat some catalyst inner part of this tube. So, very small diameter and then inner side coating or wash coating of the catalyst. So, that will increase the performance of the reactor, and this is the microchannel reactor, and here critical channel dimension we see 50 to 5000 micrometer. So, we had 70 millimeter, here we are having 50 to 5000 micrometer. So, because of the reductions of this tube size and the performance increases because of the loss the reduction in different mass and heat transfer losses. And here also it is laminar flow regime, and large amount of surface area per unit volume increase the overall productivity per unit volume. So, you can get more productivity per unit volume in this reactor. And then another development is monolithic reactor. So, it is like say honeycomb structure, we can say these are the number of comb or circular or the square shaped channels are made, and this is a honeycomb like structure. So, it is also similar to the micro channel. Here also we can put the catalyst loading inside and wash coating, and only the improvement in the design is available in this case. And long parallel and usually straight channels and catalyst wash coated walls, and physical properties of monolith depends on specific requirements of process, and good thermal conductivity for rapid heating and of wash coat, and wash coat thermal expansion of same order of magnitude as the support, and cell density. Here what is the cell density? As you see here in this case, so number of cells are there. So, that is CPSI, that is channels per square inch, channels per square inch, that is very important, that will decide the dimensions of the channels also. So, that influences the performance of the process, and CPSI is 1 by D channel square in inch. So, 3 modeling zone, the gas to the interior of the channel, wash coat and channel wall. So, these are 3 parts, this one and in between. Now, comparison of different reactor types. If we compare, then fixed bed and tubular 700 to 950 degree centigrade, 10 to 25 bar, and regular irregular packing materials, racing rings are used, and high production capacity it has, and less heat transfer efficiency, as we are talking about the limitations is reduced by the reductions of the diameter of the tubes, and then larger footprint, and catalyst deactivation starts at 700 degree centigrade. Okay. Then we see micro channel, the temperature is given here, that is 15 bar and 860 to 900 degree centigrade, the wash coated catalyst, and we uniform temperature, low rate of excess air reduces the cost of blower or compressors, their requirement reduces, and then thermal losses below 5% for scaled up plant, and then it requires advanced technology. This technology is not very matured, some plants have come up and it is still development stage, and small it is having small capacity also, and many reactors can be arranged in parallel for high throughput. And the monolithic also the similar operating conditions it is having, and same type of catalyst is also used, and it is also similar properties, low pressure drop, good mass transfer interface, and good thermal and mechanical properties, simpler scale up due to specific geometries. And here these are the disadvantages, that is ceramic monoliths have poor thermal conductivity, hence metal monoliths are preferred. Up to this in this class, thank you very much for your patience.